So in the last talk, we described Model 1, which is a purely depolarizing for both the incident and detected sources. That's not as common of a model as is typically used for describing second harmonic generation, because typically the second harmonic generation that comes in is generated by, even if there is some polarization lost for the fundamental light, it's still only the ballistic light that contributes to the SHG, and typically that's still going to be assumed to have a reasonably well-defined polarization state. So if we assume that the light coming in retains at least the component that generates signal that we see, retains its pure polarization state, then it's really just depolarization of the SHG that we detect, and that can contain two contributions: the direct coherent second harmonic generation that we want, and also the scattered contribution, and that can be measured either in the co-propagating with the second harmonic generation or non-co-propagating. Now, the reason the second harmonic generation is the scattering of the SHG is more relevant than the scattering of the fundamental is twofold. First of all, it's shorter wavelength, so it's more prone to scattering in most media. Second, we detect all of the SHG, whereas only the unscattered component of the fundamental contributes to the detected signal. So today, next, we'll be talking about Model 2, which is really arguably more common for a model describing a source embedded in a turbid medium. So how do we handle this? Well, if the incident light, we may have losses, but as long as the incident light still retains the polarization state that it had at the far field, then the Stokes vectors driving the process are still unaffected. And so we can think of the second harmonic conversion of process as still arising from a coherent interaction. And in fact, the only thing we have to worry about is the Mueller matrix. This is now the linear Mueller matrix describing the loss in polarization purity from the SHG that is initially generated and then also has contributions that are depolarized, so that we can consider both the purely polarized and depolarized components by just linear propagation of the SHG, assuming that everything right here at the source initially starts out purely polarized. So this actually turns it from a nonlinear problem into a linear problem. You still have the nonlinear optics describing the coherent frequency conversion, but then the depolarization can be handled based solely on a linear Mueller matrix. So if we do this, we can again take advantage of the fact that the degree of polarization is our friend here and can help provide a measurement of that parameter alpha. And if we take and invert, this is now the purely polarized component, if we just look at and add together these two terms in the scattering component and the scattering alpha, this is, again, if we go back to the early discussion, the very first discussion on Mueller matrices and Mueller tensors, where we reviewed linear effects. This is effectively the Mueller matrix that was derived for handling partial depolarization from optical scattering, and upon linear propagation through a turbid medium. So if we take and think of the total net Mueller tensor as just the product of what we had for pure polarizations multiplied by this linear propagation term, then that gives us a good model, and we can get alpha from the degree of polarization. And that allows us to invert the system fairly readily. Again, we'll use one illustrative measurement that describes a broad class of possible measurements, and that's one where we're doing polarization rotation. So if you are measuring light intensity on the horizontal detector, for example, you'll measure that as a function of the polarization state of light coming in. We're assuming linearly polarized light because that's the most straightforward one to generate and to manipulate. And you can look at any subset just by choosing a value for gamma. If gamma equals 0, then this is going to correspond to horizontally polarized light, and you'll be probing that term individually. If gamma is 90 degrees, you have pure vertically polarized, and so forth. So you have these different combinations you can access. And in general, if you make measurements as a function of the rotation of gamma, the most you can pull out are these 5 elements, and they're related back to the Jones tensor elements through to these expressions here. These are the Jones tensor elements describing the purely polarized component. If we want to generalize it and include the depolarized component, it's actually not that bad. So if we think of the total set of 10 observables as consisting of the first 5 for the horizontal detector and then the second 5 for the vertical detector stacked on top of each other, then depolarization and these are purely polarized. Depolarization is just going to sort of scramble the intensities on these two detectors. And so what we can think of it as just basically being a depolarization. We're going to take these 5 and start leaking some of them into this set of 5 channels and vice versa. And so we'll have one component that corresponds to what we started with, and another component that corresponds to the detection for the horizontal will really just be the average of the light that was generated from both the horizontal and vertical initial polarizations and then propagated to the polarizer. So this would correspond to the purely depolarized component. This is the purely polarized component. We can just turn this into a simple matrix notation, and now we have the observed. This is a Kronecker with the 5-fold identity matrix. So we've got this set, and then repeat that 5 times basically to pull out all the different tensor elements for A. In the local frame, if we want to recover, if the goal is recovery now of the local frame Jones tensor, then we can invert the observables using this expression. As long as it's sufficiently overdetermined, if we have enough measurements and a small enough number of free parameters for the local frame tensor elements, we can either invert this by linear algebra, or we can do a nonlinear fit to pull out the most probable values for the local frame tensor elements, because they're all given as products here. We can do the exact same thing. We can just expand this all the way down to the molecular frame if we want, using the architecture previously described for treating the purely polarized components in Jones matrix, in the Jones tensor framework. If we want to do measurements not using a polarizer here, but instead replacing this assembly with something that does fast polarization modulation, like an electro-optic modulator or a photoelastic modulator, the math remains almost identical. In fact, the only thing that changes in all of the description that was just provided is the definition of P. And you can look up in the textbook what those turn out to be in terms of the individual entries. You really just bring in some complex values for P, so it's not all just 1s and 0s. There's some i's and negative 1s in there. But otherwise, nothing else changes in the rest of the mathematics for phase modulation as opposed to polarization rotation. And that seems like a great place to stop.